Hello everyone, I'm Yue from University of Pennsylvania. Today I'm going to talk about our recent findings on the PathFinder routing algorithm. Routing is the last step in the FPGA compilation process. Here we borrow the animation provided by VTR project to visualize the routing process. Simply say, this process tries to find the shortest routing path for all interconnections under the tight routing resources constraints. PathFinder is one of the most popular algorithms used for the routing process. In this algorithm, the routing resources is represented by a directed graph. In this directed graph, each node represents a programmable unit in the FPGA device, such as the CLB, and each edge represents a while with a routing latency. A connection is defined by a pair of source and sink. In this example, there are three interconnections, S1 to D1, S2 to D2, and S3 to D3. The goal of the routing process is minimizing the routing latency to maximize the operating frequency. So it is easy to find that all three interconnections will be routed through node B to achieve the minimum routing latency. However, this leads to an overutilization of node B, which we call routing congestion. Routing congestion is the major problem need to be solved by the FPGA router. And the PathFinder algorithm provides a negotiation-based congestion router to resolve routing congestion. Specifically, it defines a cost function for each node, and the path with the lowest cost will be chosen to route a given interconnection. The routing process is performed in an iterative manner, and all interconnections will be rerouted in every iterations. And the cost of each node will be updated at the end of each iteration, and this iterative process will be terminated when no node is overutilized. It is easy to show that the delay should be included in the cost function to minimize the routing latency. However, as we showed in the previous slide, only include delay in the cost function will lead to the routing congestion. This type of routing congestion is defined as the first-order congestion problem in the PathFinder routing algorithm. To resolve this type of routing congestion, PathFinder algorithm introduced the coefficient Pn into the cost function. This coefficient Pn is calculated using Xn. Xn is the number of interconnections routed through a given node, and the P base increases after every iteration. Here we will show the routing process to illustrate how this Pn can resolve the first-order congestion problem. So in the first iteration, P base is small, and we first route the interconnection from S1 to D1. At this time, no interconnection is routed, so Xn is 0 for all nodes, and the Pn is 1 for all nodes. So this interconnection will be routed through node B. Then we will route the interconnection from S2 to D2. We can see that the Xn for node B is 1, which increases the Pn for the node B. But since the P base is small enough, so this small increase does not change the routing result, and S2 to D2 is still routed through node B. And then we route the interconnection from S3 to D3. We can see that at this time, the Xn for node B is 2, but since P base is still small enough, so S3 to D3 is routed through node B. Then the P base will increase at the end of this iteration. And when P base is large enough, we can see that the interconnection from S2 to D2 will be routed through node A, and the interconnection from S3 to D3 will be routed through node C. Then we can see that using the coefficient Pn can resolve the first-order congestion problem. The PathFinder routing algorithm then defines a second-order congestion problem, which cannot be resolved by using the Pn alone. we can see that when we route S2 to D2, since no interconnection is routed at this time, so xn is 0 and the pn is 1 for all nodes. So no matter how large p base is, the interconnection from S2 to D2 will be always routed through node C. And the interconnection from S3 to D3 will also be routed through node C since it has no other choice. Then using Pn alone cannot resolve the congestion on node C. To resolve this second-order congestion problem, PathFinder algorithm introduced the coefficient Hn into the cost function. The Hn of the overutilized nodes increases after every iteration. So we can see in the first iteration, the S1 interconnection S1 to D1 will be routed through node B, and S2 to D2 will be routed through node C, and S3 to D3 will be routed through node C. So the node C is overutilized in this iteration, and the HC will be increased after this iteration. And when HC is large enough, we can see that the interconnection from S2 to D2 will be routed through node B. This leads to an overutilization of node B, so the HB will increase after this iteration. Then we can see that because the increase of the HB, the interconnection from S2 to D2 will be routed through node C again, and this leads to the overutilization of node C. And it is easy to show that the H coefficient HB and HC will be alternatively increased in the following iterations. And when HB is large enough, we can see that the interconnection from S1 to D1 will be routed through node A, and the interconnection S2 to D2 will be routed through node C, and S3 to D3 will be routed through node C. So using Hn can resolve the second-order congestion problem. So this is the background on the PathFinder routing algorithm. In the remaining part of this presentation, we will show that these two types of routing congestion problem are not appropriately defined in the PathFinder routing algorithm, which leads to two problems and reduce the routing quality. We then redefine these two routing congestion problems to enhance the PathFinder algorithm, and this enhanced PathFinder algorithm is evaluated using VTR8. So the first problem is that the routing quality of the PathFinder algorithm depends on the routing order. We will use the first-order congestion problem to illustrate this routing process, this issue. And as we showed in the previous slides, in the first iteration, all three interconnections will be routed through node B. And here we assume that the P base is increased to 3 in the second iteration. And we route the interconnection from S1 to D1 first. It will be routed through node B since no interconnection is routed at this time, and Pn equals to 1 for all nodes. And then we will route this interconnection from S2 to D2. At this time, since P base is large enough, so Pn is very large for the node B, and the interconnection S2 to D2 will be routed through node A. And then we will route the interconnection from S3 to D3. Similarly, the Pn for the node B is large enough, so S3 to D3 will be routed through node C. So we can see under this routing order, the longest critical path delay is 6. Now let's try another routing order. If we route the interconnection from S3 to D3 first, it will be routed through node B. And then we will route the interconnection from S1 to D1. Since the Pn for node B is large, so this interconnection will be routed through node A. So finally, we will route the interconnection from S2 to D2. The Pn for node A and B are large, so this interconnection will be routed through node C. And we can see that under this routing order, the longest critical path delay is 8. This means that the routing quality varies under different routing orders. Since it is very hard to find the optimum routing order, so it is also very hard to get the optimum routing quality. The second problem is that this two routing congestion problem does not well justify the necessity of introducing the coefficient Pn, since both congestion problems can be resolved by using Hn alone. So let's take a look on the first order congestion problem first. So in the first iteration, all three interconnections are routed through node B. This increases the coefficient Hn for node B. And when HB is large enough, we can see that the interconnection S2 to D2 will be routed through node A, and the interconnection S1 to D1 will be routed through node A, and the interconnection S3 to D3 will be routed through node C. We have an overutilization of the node A, and this increases HA. And when HA is large enough, we can see that S2 to D2 will be routed through node B, and S1 to D1 will be routed through node A, and S3 to D3 will be routed through node C. So using Hn alone can resolve the first order congestion problem. For the second order congestion problem, we do not show the intermediate routing iterations for simplicity, but when HB and HC is large enough, we can see that S1 to D1 will be routed through node A, and S2 to D2 will be routed through node B, and S3 to D3 will be routed through node C. So we can see that using Hn alone can resolve both first order and second order congestion problem. So in this presentation, we redefine the two routing congestion problems and provide a new cost function to resolve these two problems. So first, we reuse the first order congestion problem defined in the original PathFinder algorithm, but we propose to using Hn alone to solve this congestion problem. Then we introduce a new second order congestion problem for introducing coefficient Pn. This new second order congestion problem cannot be resolved by using the coefficient Hn alone. We can see that in the first iteration, both interconnection will be routed through node B. This increases the HB at the end of this iteration. And when HB is large enough, both interconnection will be routed through node A, and this will increase the HA. And when HA is large enough, we can see that both interconnections are routed through node B again. So we can see that this iteration process does not converge if we only using the coefficient Hn. So we will introducing the coefficient Pn to resolve this new second order congestion problem. The basic idea is using Pn to create a gap, create a cost gap for different paths. So the interconnection from S2 to D2 will be routed through node B instead of node A. And we can see that this new second order congestion problem does not require the P base to increase after every routing iterations. So P base can be set as a constant to eliminate the routing variation under different routing orders. So we use the VTR8 as the baseline in the evaluation. In VTR8, P base increased exponentially. So the routing quality of VTR8 largely varies under different routing orders. And our enhanced PathFinder algorithm can be implemented in the VTR8, and the detailed integration method can be found in our GitHub repo. VTR7 benchmark set are used in the evaluation. The three largest benchmarks are not included in the evaluation since they have a very long routing time for both baseline and our enhanced PathFinder algorithm. We first collect routing results of 200 randomly generated routing orders, and we calculate the standard deviation of the critical path delay, and this is normalized to the baseline. So we first find that the enhanced PathFinder algorithm can reduce the variation in the routing quality by 86% on average. We also know that VTR8 provides a multi-convergent routing approach to reduce the routing quality, to reduce the variation in the routing quality. In our evaluation, this approach can reduce the variation by about 20% on average. But we also find that this multi-convergence routing approach cannot consistently reduce the variation for all benchmarks. This is the scatter plot of the routing results under 200 randomly generated routing orders. We first find that our enhanced PathFinder algorithm can route the design under at a narrow routing channel width. This indicates that the enhanced PathFinder routing algorithm is more effectively in using the routing resources compared with the original routing algorithm. We also find that under the same routing channel width, our enhanced PathFinder algorithm can largely reduce the critical path delay compared with the original PathFinder routing algorithm. This indicates that our enhanced PathFinder routing algorithm not only reduce the variation in the routing quality, but also improve the routing quality. For the routing time, our enhanced PathFinder routing algorithm achieves a comparable or even a shorter routing time for about half of the evaluated benchmarks compared with the original PathFinder algorithm. And the slowdown is less than 3x for most remaining benchmarks. This indicates that the relationship between routing time and the routing quality is not a simple trade-off, and we will perform additional exploration on this relationship in our future work. We also collect the routing results and the success rate under different routing channel widths. The trend is as expected for most benchmarks. So large channel routing width leads to a shorter routing critical path delay. But we also find that for some benchmarks, when providing more routing resources, the longest critical path delay increases. And for some other benchmarks, the design cannot be successfully routed when providing more routing resources. This unexpected behavior happens in both baseline and our enhanced algorithm. We will perform additional exploration on this unexpected trend in our future work. We would like to thank Professor Andrew DeHong for his valuable technical feedback, and thank you for listening.